Hello, dear listeners. Welcome back to another episode of the Deep Dive Podcast, where we explore the wonders of the universe, one intriguing topic at a time. I'm your host, Ben, and today we're diving into a world where ancient mathematics meets modern technology. A place where prime numbers not only fascinate mathematicians but also safeguard our digital lives. Imagine a number so large that writing it out would stretch for miles. A number that holds secrets crucial to the security of your online banking, emails, and even national defense communications. Yes, we're talking about prime numbers and their pivotal role in encryption, particularly in systems like RSA. And guess what? An amateur mathematician has just discovered the largest known prime number, a behemoth spanning over 41 million digits. So grab a comfy seat, maybe a cup of coffee or tea, and let's embark on this numerical adventure together. Let's start with the basics. Prime numbers, those mysterious integers greater than 1 that are divisible only by 1 and themselves. They might seem simple, but they've been a source of fascination for mathematicians for millennia. Think back to your school days. Remember learning about numbers like 2, 3, 5, 7, and 11? These are the building blocks of the numerical world, often referred to as the atoms of mathematics. Just as atoms combine to form molecules, prime numbers combine to form all other integers through multiplication. This fundamental concept is known as the fundamental theorem of arithmetic. But primes aren't just academic curiosities. They've leapt off the chalkboard and into the very fabric of our digital society. How, you ask? Well, that's where things get really interesting. Enter the realm of cryptography, the art and science of securing information. In today's digital age, cryptography is essential. It protects our credit card information when we shop online, secures our communications, and safeguards sensitive data from prying eyes. At the heart of many cryptographic systems lies a clever trick involving prime numbers. One of the most famous examples is the RSA encryption algorithm, named after its inventors Rivest, Shamir, and Adelman. Here's the gist of how RSA works. First, we gotta talk about key generation. It starts with two large prime numbers, let's call them P and Q. These aren't just any primes, they're hundreds or even thousands of digits long. These primes are multiplied together to produce a number n. This n becomes part of the public key that's shared openly. Now, let's talk specifically about encryption. When someone wants to send you a secure message, they use your public key, which includes n and another number e, to encrypt the message. The encryption process transforms the original message into a cipher that's unintelligible without the proper key. To decrypt the message, you need the private key, which is derived from the original prime numbers P and Q. Without knowledge of P and Q, decrypting the message is computationally infeasible. The security of RSA hinges on the fact that while it's easy to multiply two large primes to get n, it's incredibly difficult to do the reverse, to factor n back into P and Q. This is known as the prime factorization problem, and it's what keeps our encrypted data safe. But why are large primes so crucial? Because the difficulty of factoring n increases exponentially with the size of the primes. This means that even with powerful computers, cracking the encryption would take an impractical amount of time, longer than the age of the universe in some cases. So, prime numbers aren't just mathematical oddities, they're the gatekeepers of our digital privacy. Now, let's delve a bit deeper into the fascinating challenge of finding large prime numbers. Finding small primes is relatively straightforward. You can test divisibility by all integers up to its square root. But as numbers grow larger, this method becomes computationally intensive. For the enormous primes used in encryption, we need more sophisticated techniques. One such method involves probabilistic algorithms like the Miller-Rabin primality test, which can quickly determine if a number is likely prime. While not foolproof, these tests are highly reliable and efficient for very large numbers. But beyond practical applications, mathematicians have long been intrigued by the quest to find the largest known prime numbers. This brings us to Mersenne primes, named after the 17th century French monk Marin Mersenne. A Mersenne prime is a prime number that can be written in the form 2 P1, where p is also a prime number. Mersenne primes have unique properties that make them easier to work with in certain mathematical contexts, including primality testing. They've been at the center of record-breaking prime discoveries for decades. And that leads us to the exciting news of the day. An amateur mathematician and former NVIDIA employee named Luc Durand has discovered the largest known prime number to date, 2 to the power of 136,279,841. This number is colossal. It contains 41,024,320 decimal digits. To put that into perspective, if you were to write this number out by hand, 1 digit per millimeter, the number would stretch over 41 kilometers, or about 25 miles. Durand achieved this remarkable feat using a free program called the Great Internet Mersenne Prime Search, or GIMPS. GIMPS is a collaborative project that uses the idle processing power of thousands of volunteers' computers worldwide to search for new Mersenne primes. What's particularly fascinating is that Durand harnessed the power of thousands of graphics processing units, GPUs, across 24 data centers in 17 countries. GPUs, commonly used for rendering video games and mining cryptocurrencies, are incredibly efficient at performing the complex calculations required for primality testing. This discovery not only sets a new record but also marks a significant shift. It ends the 28-year reign of ordinary personal computers finding these huge prime numbers, showcasing the potential of distributed computing and collaboration. But you might be wondering, what practical use does a 41 million digit prime number have? Well, in terms of everyday applications like encryption, primes of this size aren't currently used. However, the techniques and technologies developed to find these massive primes can have broader implications, pushing the boundaries of computational mathematics and inspiring new algorithms and hardware optimizations. So, what does this mean for the future of encryption and our digital security? First, it's essential to recognize that the discovery of larger primes doesn't directly threaten current encryption systems like RSA. The primes used in RSA are large but not nearly as enormous as the newly discovered Mersenne prime. However, the ongoing quest to find larger primes drives advancements in computational methods, which could indirectly impact cryptography. Moreover, there's a looming technological horizon that could upend our current encryption methods: quantum computing. Quantum computers operate on principles fundamentally different from classical computers, leveraging quantum bits or qubits that can exist in multiple states simultaneously. With algorithms like Shor's algorithm, a sufficiently powerful quantum computer could factor large numbers exponentially faster than classical computers. This capability could potentially break RSA encryption by efficiently solving the prime factorization problem. But don't panic just yet. The field of cryptography is already preparing for this eventuality. Researchers are developing post-quantum cryptographic algorithms that rely on mathematical problems believed to be resistant to quantum attacks, such as lattice-based, hash-based, and multivariate polynomial cryptography. In the meantime, the discovery of massive primes like the one found by Durand serves as both a celebration of mathematical curiosity and a reminder of the dynamic landscape of digital security. Let's take a moment to appreciate the journey we've been on today. We've traversed from the ancient realms where prime numbers were first studied as mathematical curiosities, through the development of RSA encryption that secures our digital communications, to the modern-day quest of discovering ever larger primes. Prime numbers are a beautiful example of how pure mathematics can have profound practical applications. They're a bridge between the abstract and the concrete, the theoretical and the practical. They remind us that even the most seemingly esoteric concepts can become the linchpins of technology that underpins our daily lives. The collaborative effort behind GIMP's and Durand's discovery also highlights the power of global cooperation. It shows that significant advancements don't always come from large institutions or well-funded labs. Sometimes, they come from passionate individuals and communities united by a common goal. So, whether you're a math enthusiast, a tech professional, or someone who just enjoys a good story about human ingenuity, there's something profoundly inspiring about this achievement. Well, that brings us to the end of today's episode. I hope you've enjoyed this deep dive into the world of prime numbers and encryption. It's incredible to think about how these ancient numbers play such a critical role in our modern, digital lives. Until next time, keep pondering the mysteries of the universe, and remember, sometimes the most profound secrets are hidden in plain numbers. I'm Ben, signing off. Stay curious, my friends.